Alright, let's get started. So how many were you in the last class? It was last lecture. It has been more than a week. So we started on unit 2. We started canal irrigation. So do you remember what we discussed? We looked at classification of canals. So how do we classify canals? And then we also looked at parts of a canal system. And now we are going to start on designing a canal system. And of course, we'll have some activities in the class as well. So do you remember this? Lined canals and unlined canals. Do you remember lined and unlined canals? So unlined canals are, we do not have any protection for the sediment, whereas lined provide either concrete or brickwork to protect from erosion. So what happens in unlined canals? So what do we have as base material? So what is the base material for unlined canals? So it's going to be sediments, right? So on the bed, it's going to be sediments. Now what happens when the flow has high velocity that is flowing over the sediments? Erodes. So now we are talking about sediment transport. So what is sediment transport? When the flow has high velocity, then it starts to remove the sediment particles from the bed, and it is going to cause erosion or scouring. So what are the problems of erosion or scouring in the canals? So what could be the potential problems when there is erosion? So the depth changes. And what happens if there is a deposition of sediment? So let's say the sediment is being eroded from some location in the canal and it has to deposit somewhere else. So then what happens when it is deposited? So this was our original channel and there is erosion here, and then somewhere here there is deposition. So if there is a flood, then the depth in the channel has reduced. So there would be overtopping or inundation along the channel. And what about the maintenance cost? So if there is a continuous erosion and deposition happening, then you need to continuously monitor the channel and you need to make maintenance to make sure the bed is horizontal, not horizontal, but plane. So these are the problems with sediment transport. And to avoid these problems, we are going to see actually how the sediments start to move. And once we understand how the sediments is moving, then we will design a channel so that the sediments are not moving. So we are going to design an unlined canal today. So when we have sediment particles, of course, they are going to be tightly packed. So we have some sediment particles. So usually there are three modes of transport for the sediment. So one is if the sediments are moving close to the bed. So it could be jumping, or it could be just sliding, or it goes into suspension and then it comes back again. So all of this happens within the short distance from the bed. Let's say it's all happening within this distance. So this is bed load. Because the main transport mechanism is happening close to the bed. And what about cohesive sediment? So these are, let's say, sand particles where there is no cohesion. Now, what about cohesive particles which are very fine? So if the particles are very fine, what about the weight of the particle? So the weight of the particle is going to be less. So if the weight of the particle is less, then it can get easily suspended in the water column. So the fine particles are going to move within the water column. So these are called suspended load. And then if there are particles much finer, they would be traveling as wash load. So generally we can quantify bed load and suspended load, but wash load is very difficult to quantify because they are very fine particles. So these are the three different mechanisms of transport for the sediments. Now let's say this is a sediment particle. So that is on the bed. What are the forces that are going to act on this particle? Let's say we have a fluid that is coming in here with velocity u. So what would be the forces on this particle? So the weight, somebody said lift, and what else? Right? And what else? So it is underwater. So buoyancy. And any other force? So let's say this is turbulent flow. So what else could be the resisting force here on the bed? Friction. And if it is an unsteady flow, so this represents a steady flow. So what is a steady flow? So you might have heard this term, steady flow. Time. So whatever the discharge or velocity is coming in is constant with time. So what about unsteady flow? Changes. So then we have acceleration with respect to time. So let's say we have a body at rest and we are trying to suddenly move it with such an acceleration. So what force do you expect? Inertial force. So these are the forces that act on a sediment particle. Now, can we do a balance of these forces? So we want to balance the forces that are disturbing the particle and the forces that are resisting that disturbance. So what would be the balance equation? So what are the disturbing forces? So the drag force is a disturbing force, and inertia and any other disturbing force in the horizontal friction. So it is balanced by friction. So how do we get friction? Mu times the normal force, right? So what is the normal force in this case? So the bed is horizontal. Then what is the net normal force? Normal is at what angle? Normal to the bed. So normal to the bed is at right angle, right? So this is our bed, and the normal force would be at right angle. So what is the balance in the vertical? We have one downward force and then two upward forces. So W is acting downward, and then FL and buoyancy are acting upwards. So this is the net vertical force. Now, to simplify things for our case, let us say we are looking at steady flow, and let us assume the lift force is negligible. So if it is a steady flow, then we would not have any inertial force. So this Fi component would become 0, and we are assuming the lift force is also negligible. So we are eliminating two forces for our 10 minutes. So now our FD would be mu times W minus B. So what is the drag force? Let us say this is a sphere. So what is the drag force on a circular object? So the drag force is half rho A U square, and then you have CD. What about the weight? What would this be? W minus B. Weight is mg, and mass is rho v. So this is rho vg, and rho is the density of the sediment particle. So we are talking about weight of the sediment. Now what about the buoyancy force? So that is rho w vg. So it is the weight of the water being replaced by the same volume as the sphere. So this is what we have. Now we need to further simplify this. Have you heard of Reynolds number? So what is the expression for Reynolds number? Rho Vd by mu. Or Vd by mu. So this is the Reynolds number. Now this is a Reynolds number, let us say, for the fluid. Now if we are considering the sediment particle, so this is called particle Reynolds number, represented by Re star. And that is represented as a function of the fluid shear velocity, the diameter of the particle, and the kinematic viscosity. So this is the particle Reynolds number. Now have you heard of log law for velocity? Logarithmic law for velocity distribution. So let's say this is the, what is this? So from the bed, it is increasing non-linearly. So this velocity distribution you might have seen this equation in fluid mechanics. Do you remember? From log law. So I'm representing V by V star in terms of RE star. So this on the right hand side would become a function of RE star, right? So V by V star is a function of RE star on the right hand side. So I would represent that as some factor, multiply that with RE star. So what would V be? So this is what you get for V. What about the drag coefficient, CD? What does it depend on? Reynolds number. So you might remember the CD curve where you have the Reynolds number on the horizontal axis and CD on the vertical axis. And for a sphere, it would look like this. So CD is a function of RE. So what is RE again? It is VD by. So in this, I'm going to replace V with this term. So what does this become? Can you group any of the terms in this? So this again is RE star. So this is a function of F1 times RE star squared. So this function I'm going to say again as a factor, some F2, F1, RE star squared. Now I'll go back to this equation now. what is the area of circle? Area of a circle. So in terms of the diameter, pi d square by 4, right? Now, usually the sediment particles are not spherical, so they're not ideally spherical, right? So they have irregularities. To account for that, I'm going to take this and I'm going to bring in a factor to account for the irregularities that deviate from the spherical shape, that is K1, CD rho. So this is what you have on the right hand side. So on the right hand side, we have mu OS minus rho Vg. So again, V, we can use Re star. Now I will divide by rho and multiply by rho. So this would be the specific gravity. Now can you simplify this again by replacing V with this term? So what? So if you simplify that, I want you to come to an expression where on the right hand side you only have some function of Re star and all the terms on the left hand side. So can you simplify this? Actually, that is the volume, not the velocity here. So this is the volume of the sphere. So what is the volume of a sphere? So it is a function of d cube, and you have some factor. I bring in some factor. So your right hand should only have Re star, some function of Re star, and all the parameters on the left. So use this for CD. So this is what you would get. So on the hand side, you would have some function of RE star. So all the constants K1, F1, F2, K2, all of them you can take it to the right hand side. So you have some function of RE star. And on the left hand side, in the numerator, we have rho multiplied by B star square. And in the denominator, we have gamma W S minus 1 divided by D. Now, does it similar? The numerator, you might have seen this in fluid mechanics. Shear stress. Shear stress is function of velocity square, half rho u square. So this represents the shear stress, and then this is the resisting force or the resisting stress. So this is what you would get, tau, which is the shear stress, divided by gamma S minus 1 D. And this term is theta. So this is called Shield's parameter. So this is called Shield's parameter. So generally, when we design canal, we know the flow conditions and what is the sediment size, and we estimate what is the Shield's parameter for the given flow conditions and the sediment size. And we will make sure that this Shield's parameter is within some limiting value, so that there is no erosion of the sediments. And generally, we want to maintain this theta to be less than or equal to 0.056. So when you calculate theta for a given condition, if it is exceeding 0.056, that means the channel is prone to erosion. And what if theta is just 0.056? So theta equals exactly 0.056. Limiting condition or the critical condition when the sediments will just start to move. So the sediments will just start to move when the theta hits 0.056. The stress for this theta is represented by tau c, and this is called critical shear stress. So tau is the actual shear stress for a given condition, and this is the critical shear stress at which the particles will start to move. So what happens if tau is more than tau c? So there would be erosion. And what is the expression for shear stress? You might have derived this in open channel flows. Gamma Rs. So R is the hydraulic radius, and S is the slope of the channel. So that gamma Rs should be so this theta should be less than or equal to 0.056. So gamma is unit weight of water. Now, if the specific gravity is 2.65, so if the specific gravity is 2.65, what would be the limiting value for D in terms of Rs? So what would be the relation between D and Rs? Zero. 9. And is it less than or greater than? So this is the limiting value for the sediment size. So if we do not want to see erosion in the channel, then the sediment size should be more than this. Now what we saw was on a horizontal bed or on the plain bed of the channel. But what happens on the side slopes? If the channel has an trapezoidal section, so do you think the force required to move the sediment is higher or lower compared to on the bed? So what would be the relation between the shear stress required on the slope compared to the shear stress required on the bed? So can you think of the forces, disturbing forces? Is there any additional disturbing force or any additional resisting force? So earlier, the resisting force was from the weight. So friction, which would be a function of the weight on a horizontal bed. What about on the slope? You would have some weight component that is trying to disturb the sediment. So yes. So if you compare the shear stress required from the flow, that would be less than the shear stress required on the bed. So the flow does not need to put much force on the side slope because the weight of the particle itself is trying to disturb the particle. Why not? So who has the sheet? Okay, let's not disturb the class. You can sign and leave if you want. If anybody don't want to be in the class, they can sign and leave. I don't care. Just don't disturb the class. So this is the ratio for tau c on the banks compared to the tau c on the bed. And generally, if you look at what is the shear stress on the banks compared to the shear stress on the bed, so it is 0.75 times the shear stress on the bed. So if you calculate this as gamma RS, the shear stress on the sides is going to be 3/4 of what is on the bed. So phi is the angle of friction for the soil, angle of internal friction. Now, before I leave you, now we will do a small activity. So, how many of you are appearing for placements next year? Or how many of you are interested to appear for placements? Only one? Okay, so it doesn't matter whether you want to appear for placement or not. So whatever the profession that you want to do, I want you to think of 3 skills that are required for your job that you already have. 3 skills that you need to develop over the next 1 year. Because you are in the 3rd year and within 1 year you will be out of here. So I want you to think of those 3 skills that you already have and 3 skills that you want to develop. And I'm going to make a post on Classroom. So each of you, I would like you to comment on it. So what are the 3 skills that you have, 3 skills that you want to learn in the next 1 year? So it's on the app. If you have the app, I've just posted on the app. You need to comment on it. So it doesn't have to be for placement session, whatever profession that you want to be. I want you to comment on this so that throughout the semester, you can go back to it and see how much you have progressed on improving those skills. So at the end of the semester, we'll ask it again and see how many of you have acquired those skills or some of them. So it could be communication or leadership skills, written skills, writing skills, public speaking. Leading a team or being a good team member. So what are the three that you want to enhance? Do you have a class after this? Yes. So you can keep the comments coming on the post. I'm gonna leave for today. Thanks.